We are given a rigid diatomic gas at this temperature. We need to find the angular root mean square velocity. So RMS angular velocity we need to find of a rotating molecule if its moment of inertia is I, which is given. So let this be the diatomic molecule. So its moment of inertia is clearly about one of these two axes, either x-axis or z-axis, because moment of inertia along this axis is going to be 0. So let's read that. In a diatomic molecule, rotation causes significant energy contribution along two axes only as shown. Therefore, it has only two rotational degrees of freedom. And also its moment of inertia about both x and z axis is equal. So by the law of equipartition of energy, each degree of freedom gets the energy of half kT. So we are talking about rotational energy. So there are 2 degrees of freedom. So the total rotational energy is 2 times half kT. And that we can write in the form of half I omega x square plus half I omega z square. So this simplifies to half I omega x square plus omega z square is equal to kT. Now this velocity is omega RMS whole square, which we are required to find, angular root mean square velocity. So if you are wondering why, you can compare it with how we arrived at VRMS. So VRMS square was Vx square plus Vy square plus Vz square. And our kinetic energies associated with each of these x, y and z axis was half mvx square, half mvy square and half mvz square, which you can see will come to be half mvrms square. And because each of them will correspond to half kT, so if you write, and we know vrms is 3 kT by root 3 kT by m, so if you put that value, you will get this as 3 times half kT. So that's what we have done here in this equation. So half I omega square plus half I omega z square is equal to 2 times half kT, and this is omega RMS whole square. So we get our answer that omega RMS is root 2 ki kT by I. All right.